In this video, I'll walk through the proof of Theorem 4.6, which establishes the fact that the connectivity and edge connectivity of a cubic graph are equal. I'll motivate this with an example and a reminder of Theorem 4.4. So let's start there. Remember that Theorem 4.4, Whitney's inequalities, established that the vertex connectivity or connectivity of the graph is at most the edge connectivity, which is at most the minimum degree of G. In particular, I want to draw your attention to this part of the inequality. And we see that, vertex connectivity is bounded above by edge connectivity. And we've actually seen an example already of a case, a graph, where this inequality is strict. So remember this example from a previous video. Here, U equal to, let's say UV1, for instance, is a minimum vertex cut. So the connectivity of the graph is equal to 2. But it requires 3 edges in order to be removed in order to disconnect the graph. So X equal to E1, E2, E3 is a minimum edge cut. And so lambda of G, the edge connectivity, is equal to 3. And so the point here is that the inequality in Whitney's theorem, Whitney's inequalities can be strict. So what Theorem 4.6 is establishing is that while the inequalities may be strict, for cubic graphs, this is not the case. For cubic graphs, the vertex connectivity and edge connectivity are always the same as each other. So let's take a look at this proof. So let's deal with a fringe case for a cubic graph. If for a cubic graph, we have that the vertex connectivity is equal to the edge connectivity is equal to 0, if and only if G is disconnected. So if it's a disconnected cubic graph, then both of the connectivities are 0 and the equality holds. Another fringe case we can deal with here is if these are both 3, or rather if the vertex connectivity is 3. If the vertex connectivity is equal to 3, then since in a cubic graph, remember this is 3 regular, and so in particular, the minimum degree of G is equal to 3. Then we would have, by Whitney's inequality, we would have 3 less than or equal to lambda of G, less than or equal to the minimum degree of G, which is 3. So the edge connectivity is also 3 in this case, and equality holds. So we have 2 cases. We know that, it has to be this vertex connectivity has to be either 0, 1, 2, or 3 because of this minimum degree. We've already ruled out the case of 0 and 3 and seen that equality holds in those 2 cases. And so for the remaining 2 cases, we have either the vertex connectivity is equal to 1 or the vertex connectivity is equal to 2. In any of these cases, we're going to establish a couple facts and then use them. So in either case, let U be a vertex cut, a minimum vertex cut. Of G. And so we have either u is equal to 1, or u is equal to 2. The cardinality is equal to 1 or 2. So these will be our two cases corresponding with these two. And either way, G minus U is disconnected. And we'll let G1 and G2 be two components of G minus U. We know there could be a possible third component here, but we'll just use G1 and G2, and I have a claim to make here. So since G is cubic, right, 3 regular, for each U in the vertex cut, at least one of G1 and G2 contains exactly one neighbor of little u. So let me try and back up this claim a little bit. So here we have our vertex cut u, and I have little u inside of here. And I know this must separate it into at least two components. So let's say G1 and G2. And of course, we could have a third component here because it's cubic. But we couldn't have any more. Remember, for this to actually be a vertex cut, every vertex in here has to be adjacent to at least one vertex in each of the components. So there's a couple things here. U could be adjacent to a vertex in each of these components, in which case, yeah, at least one of G1 or G2 contains exactly one neighbor of U. Yep, that would be true. We could also have the case where I have this vertex cut U. This looks like a face, doesn't it? Here's my little U again. Maybe I just have two components then. I mean, this would have to be the case for 3 components. You'd have to be adjacent to exactly one in each. But maybe I have the case where U is adjacent to 1 in G1 and 2 in G2, something like that. That's certainly possible. And in this case, G1 would be the component that contains exactly one neighbor of U. And swapping G1 and G2 here would also be fine. It could be G2 that contains exactly one neighbor of U. And so hopefully that justifies that claim for you. So now let's break this down into cases. So case 1, we'll assume the vertex connectivity of G is equal to our minimum vertex cut is equal to 1. And so U is a cut vertex, just contains a cut vertex. Maybe I should say consists of. Okay, in this case, I just have this would be my U is just the one vertex U, and I have at least 2 components here, but I can say by this claim above, at least one of G1 or G2 contains exactly one neighbor of U. Let's suppose it's G1. So I have G1, I have G2, and or I can just say I have the rest of the graph here. I have some other blob here, and we'll say G1 contains exactly one neighbor of U. Maybe let's call this U prime over here. Then X equal to U prime U is an edge cut of G. And we know it takes at least one edge to disconnect it, and so the edge connectivity of G is equal to 1 here, which is the same as the vertex connectivity of G. And so we're done for case 1. Case 1's not too bad. Case 2 gets a little bit trickier. So here we're assuming the connectivity of G is equal to, again, the minimum vertex cut is equal to 2. And so U, let's say U consists of 2 vertices, U and V, whose removal disconnects the graph. We're sort of going to break this up into subcases. In the first one, I'm going to assume that U and V has exactly one neighbor, say U prime and V prime, respectively, in the same component. Right? We know each is adjacent to exactly one vertex in at least one of the components. And so in this sort of subcase, we'll assume that they're adjacent to those vertices, and those happen to be in the same components. So what we have here, again, so here's my vertex cut U, here's U and V. And then let's say I have this component, and we can go ahead and assume it's G1 without loss of generality. U prime, V prime is in G1. And so they're each adjacent to their exactly one neighbor in G1, and then we have maybe the rest of the graph over here, and they have their two neighbors over there. And in particular, they could be adjacent to each other, so I don't want to draw all these, but they have at least those neighbors over there. Well, in this case, so this is U prime, V prime, then X equal to U prime, V prime is a minimum edge cut, right? That would disconnect the graph. And so the vertex connectivity is equal to 2, which is equal to, the edge connectivity is 2, which is equal to the vertex connectivity there. And so we can rule that little subcase out. We can say, so we may assume that U has one neighbor, U prime in G1, and two neighbors in G2, while V has two neighbors in G1 and one neighbor, V prime, in G2. So yeah, you might be saying, why do we only have two components here? We'll talk about that in a second. Let me try and draw the picture here. So the idea is we should only have two components, G1 and G2. And here's my vertex cut U with U and V in it. Right, so since we ruled out this earlier case, the existence of a component such that U and V each have exactly one neighbor in that component forces us into this, this situation, which forces there to not be an edge between U and V, right? Because I have to have one. Right, yeah, if there were three components, then each of U and V would have to be adjacent to a vertex in each of the components. And then we would be, in this original case, there would be one component that contains the one neighbor of U and V. So we can assume, yeah, there's only two components here, and moreover, U and V are not adjacent because we have U has one neighbor in G1. We'll call it U prime, and V has two neighbors in G1. I'm not going to name them because I don't need them. And let's see, U has two neighbors in G2, and V has just one neighbor in G2. So I'll call that V prime. Now, since we have this situation where U and V is not an edge, so notice, yeah, UV is not an edge in order for us to be in the situation. Hence, X equal to, again, we'll remove U prime, V prime, those two edges. And since UV is not an edge, G minus X is disconnected. is disconnected. And so X is a minimum edge cut. And we have that the edge connectivity is equal to 2, which is the same as our vertex connectivity here as well. Oops. And that proves the theorem. So for any cubic graph, the vertex connectivity and edge connectivity are exactly the same, or the same value. I'm not going to prove this theorem, but I'm going to mention it. So we've also seen the other part of this Whitney inequality, that the edge connectivity is at most the minimum degree. What this establishes is a class of graphs for which that part of the inequality is exact, is actually an equality. And that is the case when we have a connected graph of diameter at most 2. So for any of these graphs, edge connectivity and minimum degree are exactly the same. Again, I'm not going to prove that, but hopefully you'll be able to use this if you need it for a homework problem. Okay, that's it for this video, and that's going to wrap up this section. You should look at the other theorems in the section. You don't necessarily need to know how to prove them, but you should be able to use them if you need it. Okay, that's it for this.